Okay, I'm going to start by loading MATLAB. Module load MATLAB, and then MATLAB ampersand. And you note when it opens up that my file from last time is still open, but you could open your wherever you have saved that cst.m file. Open that, navigate and open that up. Takes you over to the M file here that we went through last time. We're going to go through again a little bit here. We can go ahead and run that. If we click on this file or go to the editor, hit run. Okay, and that gives us a bunch of stuff. The first thing we come to is the KG reduced matrix. We output that, so let's go see where that's done. So once we do the assembly, we create the symmetric global stiffness. We then only save the values. We apply the elimination approach. We only save the values we need. Okay. We also create the reduced global force matrix, which is here, where you can see I'm actually passing in the applied force that is a variable that I define at the very top of the program. So we then solve for UR. So that is right here because I don't have semicolons after this stuff, so it's outputting to the screen here. So we get UR, and remember these UR values are the 1, the 3, and the 4 degrees of freedom is what they correspond to. So what I do then is I need to apply those back into the global displacement vector. Okay, so that has a total of 8 nodes, and I put those in the right spot. And I actually do that manually. Okay, so we can actually first compare what we have here. Actually, that's done here. So here's the global Q. This would be the global Q, basically. So let's compare this value, the first degree of freedom. It's in the X direction, so it's 0.27778. If I go back to Abacus, we see that that value looks really good and compares well. The next thing we want to do, we can get more quantitative on this, and I'll show you that. But the one thing we want to do here is actually output the displacement for this node also, because that's the only other unknowns. That was degrees of freedom 3 and 4, right? So back here, it would be these values here, 3 and 4, which are going to be equal to 0.075 and negative 1.41. So it's tricky, though, if you look to actually figure out from the contours what the values are at this node, because they're kind of in the middle of the extremes. So it makes it very difficult. So what we can do is go quantitatively. We can actually go to XY, create XY data. And we're going to go ODB field output. We'll say continue. And then we're going to go to the unique nodal and select the U1 and U2 values. We'll select that node. So hover over, select that, say done, and then we're going to save that. Okay, so what that does, instead of plotting it, it actually saves it over on this XY. In the feature tree, you have XY data, and you see that both of those values are there. Now, you can plot those. If you right-click on this, you can say plot. Then you click on the other one, you say add to plot. So you can plot both of them, but it's still difficult to read. So what I like to do is go to report, and then I go to XY. And then what that does is report the XY data. I think we've looked at this before, but you can select both of those and just hit apply. And what you see is that a report was appended to the file abacus.rpt. So that was a file written in your current directory, wherever you created, wherever you launched Abacus from. And you can then go open that. So we will do a gedit abacus.rpt. We'll do an ampersand. And there we see that we get the U1 value for node 2 and U2 for node 2. Turns out we got lucky, because I think that if we go back to our problem, yeah, our 2 value was actually that same node. So the mesher helped us out that time. So these values, this is 0.07575, it looks really good, and the same way at negative 1.414. So these are the same values that we got back from our hand/MATLAB calculation. So the displacements look really good, they compare very well. Let's go down to the strain element, the strain of the element. So to do that, let me jump back here, talk a little bit more about that. We just finished this stuff up. Now, what we do here is create cells. So I don't think I mentioned this last time, but a cell is a unique way that MATLAB can store sort of vectors and tensor data. So up here, we actually used it for the stiffness matrix. We created a cell somewhere. Here we did a cell. A cell is 2 by 6. So actually what it's doing here, it's creating a storage block, 2 storage blocks, and each storage block is 6 long. Okay, so that's kind of a unique way MATLAB can store data. So that's what allowed us to reach in with these squiggly marks here, because we're looking at the cell. Okay, the cell, and then that value. So it gives you a 6 by 6 square value. So here we're defining cells for the stress and the strain. We have 2 cells because you have 2 elements. We have 3 values, the XX, YY, and XY, to store. Although when I look at this, I'm not sure that that's right, actually. That might be a bug, because I have to go look at this cell function. The cell is I'm not sure if that means like a 3 by 3. So for the matrix that we got for the stiffness, it gave us a 6 by 6 square in that cell position. So I'm assuming this is giving us a 3 by 3 for each cell, which we don't really need. We actually need a 2 by 2. So because we're in XY, just 2D. So I don't think it would mess us up, but that could be a bug. All right, so then what we do is we loop over the elements, and we're extracting the nodal connectivity, so the node numbers from the connectivity. We then use those node numbers to get the coordinates. Okay, so it's like nested, it depends. It's like a linked array. And then we create the Jacobian and the B matrix. Okay, we're going to need the B matrix, and this is basically why we redid the element calculation, because we need the B matrix down here. We need B times Q. Okay, and then for the stress, we need the D, so we need B, DBQ. Now, there are more efficient ways to do this, because we're recomputing a lot of this stuff. Ideally, you would actually store the B matrix, since it doesn't change, because it's based on the underformed coordinates. So there's more efficient ways of doing this in a real finite element program, but we're just kind of going through the process here. Now, we do need to extract the local displacement vector. So here we're looking at the global displacement, which is U. We're using the node 1, 2, and 3 that we got from the connectivity up here for that particular element, and we're referencing that, we're using the special counting system we talked about in the last lecture. So we extract these displacements for each node in the X and Y, and then we put those into the local Q matrix. Okay, and then we apply B times Q to get the strain and DBQ to get the stress. And then here's what we're doing. We are just plotting out the values. We're assigning, well, I didn't really even need to do this. I could have just put strain 1 and strain 2 here. The squigglies are unique, and that's for the cells. Okay, so we output that. Let's go back and see what actually gives us. Okay, so here's our strain. So this would be the XX, the YY, and the XY. Okay, so if we go back to MATLAB, our Abacus, and we go into strain, gives us a lot of these other principal things we don't need right now, but we have E11, okay, we have E22, and we have E12. If you look at it gives us E33, but it's just 0. All right, so we can also output this stuff very quickly. If we go to that, to check it, we can go to this field output, Or now let's do the strain component. So we'll do 1, 1, 2, 2, and 1, 2. We'll do that on the centroid, and we're going to select edit selection. We're going to do this element. Okay, so say done, and then save. Okay, now what happened here, I forgot to show you, but what happened here was that when I wanted to know, we got lucky with the node numbering, at least for this node, right? But this was our element 1 here and element 2. So I went in to check the node labels, right? Because I wanted to, in our case, it doesn't really matter because we select the element from the viewport, so it doesn't matter for us. But if we were to use like node element labels to actually extract the information, you have to be careful because Abacus actually numbered that number 2 and this number 1, and of course that's reverse in our hand calculation. So you have to be careful about that. In our case, it doesn't matter because I selected from the viewport. We only have 2 elements. So now we can report. We have that data up here. So we can now output that to the report. So what I'll do is I'll select this, and then I'll hit apply. And what it does, it appends it. Okay, so it doesn't overwrite it. It just appends it. So if I click on this, I have this message up here that says, it changed. Do you want to reload it? Say yes. And there we have our new strains. So the 1, 1 is here, the 2, 2 is the shear, and the 1, 2 is the shear, and the 2, 2 is the Y. So for 1, it's 0.277, 0.277. For the shear value, it's 0.2020. This is the shear, 0.2020. Looks good. And then finally, negative 1.414, and that is the 2, 2 value. So the strains look really good. Of course, the stresses is done in the same exact way. We just go back to the field output, go to uncheck that one. We'll select our 1, 1, 2, 2, 1, 2, save it. At least one, got to select the element. So edit, we'll stay with that element. Of course, you can do it for both. Save, say OK, and then go to our, see that it outputted here, that's good. The report, and then select those values and say apply. Go back to our Abacus report, reload it, and there we have our stress. So it's negative, it's negative 0.08. Stretch the strain, okay. So the XX is negative 0.08, negative 0.08 for both of those, and then the YY is this 2, 2 value, and it's negative 1.43 down here. It looks really good. So you can see that these results are really accurate. You can do the same thing for the element 2. So I think what I'll do is I'll wrap it up here, and I want you to kind of go through this at your own pace. If you need to slow down and redo it, it's really important that you understand the last couple lectures. I feel like these are really the keystone of the class because we start to put it together for more complex, cases. This is 2D. It has the isoparametric stuff. It has the hand calculation. We have to do the abacus. We actually compare them and see that they give the same result. So this is going to be a very similar. To exam 2, what we did here today. You want to make sure that you understand how to partition. Again, it's a capability, a practical capability in Abacus. So it's not even like really a fine element theory thing. It's just that I feel like it helps. It's another, it's another advanced skill in Abacus that you're gaining here. So make sure you understand about partitions and datum planes. So I'll leave it there, and I will see you next time.